What if gravity isn't a force at all, but a quiet bend in the fabric of reality itself? What if the universe doesn't pull, it simply curves? Tonight we'll drift through the silent architecture of space-time, where stars carve invisible pathways, light bends without sound, and the geometry of existence quietly shapes everything we know. If slow, thoughtful journeys into physics help you relax and think deeper, consider subscribing, and let's gently unfold the universe together. Long before equations curved space or time was woven into a single fabric, gravity lived in the human mind as something far more mysterious. A quiet, invisible pull that simply was. It required no geometry, no tensors, no warping grids stretching into the cosmos. It was experienced, observed, and accepted in the same way early humans accepted wind, darkness, or the passing of seasons. Gravity belonged to the category of forces that acted without explanation, a silent habit of the world. In ancient landscapes, long before observatories or polished lenses, people noticed the simplest expressions of this pull. Stones fell, fruit dropped, rain descended from the sky and never drifted upward again. Rivers flowed downward, always seeking some unseen low place. The ground seemed to possess a kind of authority, a quiet command that drew everything back to itself. There was no language yet for mass or attraction, only the repeated observation that what rose must eventually return. For early civilizations, this returning motion felt less like physics and more like purpose. Many believed objects fell because they sought their natural place. The earth, in this view, was not merely ground but the center toward which all heavy things yearned. A stone dropped from a hand did not fall because of force. It fell because it belonged below. Upward motion required effort, intention, interruption. Downward motion required none. It was the universe restoring order. Greek philosophers refined this belief into structured thought. Aristotle, observing the world with patient attention, concluded that every element had a natural direction. Earth and water moved downward. Air and fire moved upward. Objects fell not because they were pulled, but because they were composed of elements seeking their rightful domain. A rock dropped through the air was simply Earth returning to Earth. The explanation felt complete, even comforting. Motion had meaning, direction had philosophy. Yet even within this elegant worldview, quiet mysteries lingered. If all things sought their natural place, why did the moon never fall? Why did the stars not descend like sparks from a dying fire? The heavens behaved differently from the earth. Celestial bodies moved in perfect arcs, repeating patterns that felt deliberate rather than accidental. The sky seemed governed by laws separate from those of falling stones. So gravity, as experienced on Earth, stopped at the clouds. Above them, another system ruled, one of crystal spheres, divine order and eternal circular motion. The moon did not fall because it was fixed to an invisible shell. The planets did not drop because they were embedded in rotating heavens. The universe was layered, below the realm of falling things, above the realm of perfect motion. Apples fell, moons circled. No one imagined the two motions shared the same cause. The idea that the same invisible influence guiding a falling fruit also steered the orbit of a distant world had not yet entered human thought. Gravity remained local, earthly, intimate. In medieval times, scholars preserved and debated these inherited ideas, blending them with theological frameworks. Motion became tied not only to natural place but to divine design. Falling objects did so because the cosmos had been arranged with intention. The earth held things because it had been made to do so. Inquiry slowed, not from lack of curiosity, but from reverence. The mechanics of falling were less important than the meaning behind it, yet observation never ceased. Sailors watched tides rise and retreat with lunar rhythm. Builders saw stones accelerate as they dropped from towers. Archers noticed arrows curve downward. No matter how powerfully released, gravity revealed itself constantly through motion, but never explained its source. It was felt through muscle strain, when lifting loads, through the thud of impact, through the inevitability of descent. Then came the slow shift toward measurement. Thinkers began timing falling objects, comparing weights, studying motion not as philosophy but as behavior. Galileo, watching spheres roll down inclined planes, noticed something strange. Heavy objects did not fall faster than light ones, at least not in the way Aristotle had described. Motion followed patterns that could be measured, predicted. Still, even as understanding sharpened, the cause remained hidden. Objects accelerated downward. But why? What reached out to them? What invisible hand guided their path? The world had moved from symbolic explanations to mechanical ones, yet gravity itself remained unseen. Then, in the quiet countryside of 17th century England, the question deepened. The story, softened by retelling, speaks of an apple falling from a tree near a contemplative observer. Whether literal or embellished, the image endures because it captures a turning point in thought. The falling apple was no longer just a familiar event. It became a question. Why down? Why always toward Earth? And if Earth pulled the apple, did it also pull the moon? This was the moment gravity began expanding beyond fields and orchards into the sky itself. The realization was not sudden but gradual, like dawn light spreading across hills. If the Earth could influence objects nearby, perhaps its reach extended farther. Perhaps the moon was not fixed to a celestial sphere but perpetually falling sideways, endlessly missing the Earth because of its forward motion. This idea was radical, not because it complicated gravity, but because it unified motion. The fall of an apple and the orbit of the moon became expressions of the same phenomenon. No longer was gravity confined to Earth. It became cosmic. Yet even then, gravity was still imagined as a force, an invisible tether stretching across emptiness. Isaac Newton formalized this view with mathematical clarity. Every mass attracted every other mass. The strength depended on size and distance. Equations replaced metaphors. Prediction became possible. Planets orbited because they were pulled. Tides rose because the moon exerted influence across space. Comets curved along paths shaped by gravitational reach. The universe transformed into a system of interacting forces, each body affecting another through invisible connection. And still, mystery lingered. How could objects influence one another across empty space? What medium carried this pull? How did the Earth know the apple was there? Gravity worked flawlessly in calculation, yet its mechanism remained obscure. It acted instantly, silently, without visible messenger. So even at the height of Newtonian triumph, gravity retained its ghost-like quality. It could be measured but not seen, understood but not explained in essence. A law without a visible machine. For everyday people, gravity remained what it had always been. The reason feet stayed planted, the reason oceans did not drift away. It was constant enough to fade into the background of awareness. Only when lifting something heavy or watching something fall did its presence feel immediate. Children experienced gravity viscerally, through dropped toys, scraped knees, the thrill of jumping and returning. Builders respected it in arches and foundations. Sailors trusted it to keep seas bound to Earth. Gravity shaped behavior long before it shaped theory. And yet the deeper questions persisted quietly beneath the surface of knowledge. If gravity was a force, what produced it? If it acted across distance, how fast did it travel? Could it weaken, shield, or ripple? These uncertainties rested unresolved for centuries. Human understanding at this stage stood at an in-between place. Gravity was no longer mystical yet not fully physical. It had equations but no geometry, influence but no architecture. It described motion without describing the stage upon which motion occurred. People imagined space as empty, a passive void where forces reached across nothingness. Gravity stretched through this emptiness like invisible threads. The universe was a vast container, and gravity operated inside it. No one yet suspected that the container itself might bend. So the era before geometry was an era of intuitive gravity, felt, observed, mathematically described, yet conceptually incomplete. Apples fell, moons orbited, oceans rose, planets curved through darkness, all under the governance of a pull no one could see. It was a gravity of experience rather than structure, a gravity that acted but did not explain its medium, a gravity that connected heaven and earth without revealing the mechanism of connection. In quiet moments, watching snowfall or drifting leaves, people witnessed gravity's gentlest expressions. Motion slowed by air, descent softened by resistance. Even here, gravity whispered rather than declared. It did not demand attention. It operated continuously, patiently, and perhaps that is why it remained mysterious for so long. Forces that shout invite investigation. Forces that whisper become background. Before space-time curvature, before grids and wells and warped light, gravity was simply the tendency of things to return. The world's way of gathering itself, a universal leaning toward ground. It required no diagrams, no bending planes, only observation. Yet hidden within every falling motion was a deeper truth waiting centuries to surface. That gravity was not pulling objects through space, but shaping the space through which objects moved. But that realization belonged to a later age. In this earlier chapter, gravity remained intimate, immediate, and unexplained, a quiet agreement between matter and earth, a behavior accepted through repetition, a mystery so familiar it almost escaped notice. Apples fell without revealing why, moons circled without disclosing how, and humanity standing between orchard and sky sensed connection long before it understood geometry. Gravity in this time was not architecture. It was instinct. In the quiet centuries following humanity's first attempts to understand falling motion, gravity remained something deeply familiar, yet fundamentally unanswered. People had watched objects descend for millennia. They had built philosophies around it, timed it, measured it, even predicted aspects of it. But gravity itself, the reason things moved toward one another, remained veiled behind observation. Then, slowly, the veil began to thin. The shift did not begin with a telescope or a falling apple alone, but with a new way of thinking about the universe, one grounded not in purpose or natural place, but in mathematics. Motion thinkers began to realize could be described with precision. Paths could be predicted. Forces could be expressed numerically. The universe once interpreted through calculation. At the center of this transformation stood a quiet, intensely focused figure whose work would reshape humanity's understanding of motion: Isaac Newton. Newton lived in a world already stirring with scientific change. Galileo had studied acceleration. Kepler had mapped planetary orbits with remarkable accuracy, showing that planets moved in ellipses rather than perfect circles. The heavens were no longer divine clockwork alone. They were measurable systems. Yet even Kepler's laws, precise as they were, described motion without explaining cause. Planets moved the way they did. But why? What guided them along their invisible tracks? What held the moon in orbit rather than letting it drift away into darkness? Newton approached these questions not as isolated puzzles, but as parts of a single system. He wondered whether the motion of the heavens and the motion on Earth might share the same rules, whether the fall of an apple and the orbit of the moon were not separate phenomena, but expressions of one universal principle. This idea alone was revolutionary. To imagine that the same influence guiding a dropped stone also governed celestial bodies required collapsing the long-held boundary between earth and sky. It meant the universe was unified. One set of laws, one framework of motion, one invisible structure connecting orchard and cosmos. Newton's insight unfolded gradually, built through years of private study. He examined motion, acceleration, circular paths. He calculated how an object moving sideways while falling would trace a curved trajectory, extend that sideways motion fast enough, and the object would continually fall around the Earth rather than into it. Orbit, in this view, was perpetual falling. The moon was not suspended. It was falling endlessly, its forward motion causing it to miss the Earth over and over again. The same downward acceleration pulling apples toward soil was guiding the moon through space. From this realization emerged a profound leap. Gravity was not local. It was universal. Newton proposed that every mass in the universe attracted every other mass, not just Earth pulling apples, apples pulling Earth as well, though far more weakly. The attraction was mutual, symmetrical, woven into the nature of matter itself. This was gravity redefined, an invisible force of attraction between masses, simple in statement, vast in implication. Newton expressed this attraction mathematically through what became known as the law of universal gravitation. The force between two objects depended on their masses and the distance separating them. Larger masses exerted stronger attraction. Greater distance weakened it. With this single formulation, Newton unified terrestrial and celestial motion. The same equation explained falling bodies, orbiting planets, tidal movements, even the trajectories of comets sweeping through the solar system. It was an intellectual compression of staggering power, reducing the complexity of cosmic motion to a universal rule. For the first time, gravity was no longer just experienced, it was calculated. Planets followed predictable paths because gravitational attraction guided them. The moon's orbit could be described numerically. The pull of the sun governed the architecture of the solar system. Even irregularities, slight wobbles or deviations, could be traced back to gravitational interactions among multiple bodies. The universe became a dynamic web of attractions, each mass influencing others through invisible connection. And yet, despite its explanatory strength, Newton's gravity retained a haunting abstraction. It worked flawlessly in equations. But what was it? Newton himself struggled with this question. He could describe how gravity behaved, but not what produced it. How did two objects separated by vast emptiness influence one another? What mechanism transmitted this pull? There was no visible rope, no medium, no detectable signal carrying gravitational influence. It appeared to act instantly across space. A concept Newton found philosophically troubling. He famously avoided speculating beyond the mathematics. His position was careful, almost restrained. The equations worked. The predictions matched observation. The underlying cause remained unknown. So gravity, in Newton's framework, became what many later called action at a distance. Objects affected one another without physical contact, across the void. To some, this felt elegant, a universe governed by clean mathematical laws. To others, it felt unsettling, even mystical in its own way. The invisible pull replacing earlier philosophical explanations was still invisible, still intangible, yet its predictive success was undeniable. Using Newton's laws, astronomers could forecast planetary positions centuries into the future. Navigators could calculate lunar motion to aid sea travel. Engineers could design structures accounting for gravitational stress. The practical applications multiplied. Gravity transformed from mystery into tool, but even as it became useful, it remained conceptually incomplete. In Newton's universe, space itself was passive, an empty stage upon which forces acted. Gravity moved through this stage, reaching from mass to mass, like unseen threads stretched across darkness. Space did not participate. It did not bend, flex, or respond. It simply hosted the interaction. Time, too, was absolute, flowing uniformly, regardless of motion or mass. Gravity influenced objects moving through time and space, but did not alter the fabric of either. This framework worked extraordinarily well for centuries. It explained falling bodies, orbital mechanics, projectile motion, tides, pendulums, nearly every gravitational phenomenon observable at human and planetary scales. For everyday experience, Newton's gravity felt complete. Drop an object, it accelerates downward according to predictable rates. Launch a cannonball. Its arc follows gravitational curvature. Observe the moon. Its orbit matches calculated expectations. The invisible force, though unseen, proved consistent. Yet subtle anomalies lingered at the edges of precision. Certain planetary orbits deviated slightly from Newtonian predictions. Mercury's path around the Sun, for instance, shifted in ways that could not be fully explained by known gravitational influences. These discrepancies were small, almost negligible, but persistent. They hinted that Newton's formulation, though powerful, might not be final. Still, during Newton's era and long after, gravity as attraction between masses reigned supreme. It reshaped humanity's cosmic perspective. No longer was Earth the sole center of falling motion. Gravity operated everywhere, binding solar systems, sculpting galaxies, guiding cosmic structure. The universe became gravitationally interconnected. This view carried philosophical weight as well. If every object attracted every other, then nothing was truly isolated. Matter existed in relationship, constantly influencing and being influenced. Even the human body standing on Earth's surface participated in this universal exchange, pulled by distant stars, however faintly, while pulling them in return. Gravity became not just force, but relationship. One could feel its effects: weight, pressure, resistance when lifting, but never perceive its mechanism. Unlike wind or water, gravity left no traceable medium. It passed through vacuum effortlessly. It required no contact. It was present everywhere, detectable nowhere directly. This paradox gave Newtonian gravity a strange dual character, mathematically concrete, physically elusive. Scientists accepted that gravity existed because its outcomes were measurable. Its cause remained abstract. The elegance of Newton's formulation lay in its simplicity. A single law governing countless motions. A universal attraction shaping everything from falling rain to planetary dance. But simplicity can conceal deeper layers. Newton's gravity described how masses interacted, but not how space itself might respond. It treated the universe as static scaffolding, fixed, unmoving, indifferent. Masses moved within space, influenced by gravitational force, but space did not change in return. This assumption would later prove incomplete. Yet in Newton's time and for generations after, it felt sufficient. The equations worked. Predictions aligned. Observations confirmed. Gravity as attraction became foundational. Taught, trusted, embedded in scientific thought, it allowed humanity to calculate eclipses, predict comet returns, understand tides, design bridges, and eventually send objects into orbit. The invisible force became a navigational compass for both sea and sky. Still, in quieter philosophical corners, questions endured. How fast did gravity travel? If the sun vanished, would Earth feel its absence instantly, or after delay? Could gravity be blocked or shielded? Did it require a medium, like waves require water? Newton's framework offered no answers. It was precise in behavior, silent in mechanism, and so gravity, though mathematized, retained its whispering mystery, a force felt everywhere yet never touched. In this era, before space-time curvature, before warped grids and geometric wells, gravity stood as attraction alone, simple, elegant, immensely powerful. But incomplete. It described motion without describing the stage upon which motion unfolded. It explained interaction without explaining transmission. It unified heaven and earth, yet left the nature of connection unresolved. Still, its beauty endured. Two masses, separated by emptiness, drawn together by universal law, from drifting dust to blazing stars, an invisible architecture of attraction holding the cosmos in quiet cohesion. Newton had given gravity equation, scope, and predictive might, but the deeper structure, the possibility that gravity was not force acting within space, but a property of space itself, remained hidden, waiting for another mind, another century, another leap of imagination. For now, gravity was pull, a silent reaching across the void, powerful enough to bind worlds, mysterious enough to leave questions echoing in the spaces between them. For more than 2 centuries after Newton set his equations into motion, gravity stood as one of the most successful ideas humanity had ever produced. It predicted the paths of planets, explained tides, guided navigation, and allowed astronomers to calculate celestial events with astonishing precision. The invisible attraction between masses felt complete, elegant in its simplicity, vast in its reach. Yet beneath its success lingered quiet discomfort. Gravity, as Newton described it, acted across empty space. It reached instantly far, from one object to another, without visible intermediary. The sun held Earth in orbit through nothingness. The Earth pulled the moon across vacuum. There was no mechanism, no medium, no detectable transmission. The force simply operated. To many scientists, this action at a distance felt philosophically troubling. It worked mathematically, but what physically connected the masses? How did gravity travel? Why did it exist at all? For a long time, these questions rested unresolved, not urgent enough to disrupt Newton's triumph, but persistent enough to remain in the background of scientific thought. Then, at the dawn of the 20th century, gravity encountered a mind willing to question its foundation. Albert Einstein did not begin by studying gravity directly. His early work focused on light, motion, and the nature of time. He examined how observers moving at different speeds perceived reality. From this emerged the theory of special relativity, a framework revealing that time and space were not absolute, but intertwined and dependent on motion. Clocks ticked differently depending on speed. Lengths contracted. Simultaneity dissolved. Space and time were no longer fixed backdrops. They were flexible, relational. This realization alone began softening the rigid stage upon which Newton's gravity operated. If time could stretch and space could compress depending on motion, perhaps the universe's structure was not passive after all. Perhaps the arena of physics participated in events rather than merely hosting them. Einstein carried this intuition forward, turning his attention to gravity itself. He began with a simple but profound observation, one so ordinary it could be missed entirely. Imagine standing inside a closed elevator. If the elevator is stationary on Earth, you feel weight pressing your feet to the floor. Now imagine the elevator floating in deep space, far from any planet, but accelerating upward. You would feel the same pressure against your feet. From inside, the two situations are indistinguishable. Gravity and acceleration are locally indistinguishable. The force you feel standing on Earth and the force you feel in an accelerating frame share the same character. To Einstein, this was not coincidence, it was a clue. If gravity and acceleration were equivalent experiences, perhaps gravity was not a traditional force at all. Perhaps it emerged from motion within a deeper structure. He began reimagining gravity not as attraction between masses, but as a feature of spacetime itself. Spacetime, the unified fabric formed by space and time, was no longer rigid. It could respond to mass and energy. It could bend, stretch, and curve. Massive objects, Einstein proposed, did not pull on distant bodies through invisible force. Instead, they altered the geometry of the spacetime around them. The presence of mass told spacetime how to curve. Curved spacetime in turn told objects how to move. This was the radical shift. Gravity was no longer a force acting within space. It was the shape of space itself. To visualize this, physicists often use the rubber sheet analogy. Imagine a stretched fabric. Place a heavy sphere on it. The sheet dips. Roll a smaller ball nearby, and it follows the curved surface, spiraling inward not because it is pulled, but because the path itself is bent. In Einstein's view, planets orbit stars for the same reason. They move along the curved geometry created by stellar mass. Their motion follows the contours of spacetime. They are not pulled, they are guided. This transformation replaced invisible force with geometric structure. Gravity became architecture rather than attraction. And with this shift came profound co-nequescence. If spacetime could curve, then light, which always follows the straightest possible path, would appear to bend when traveling through curved regions. Einstein predicted that starlight passing near the sun would deflect slightly due to solar eclipse in 1919. Astronomers observed distant stars appearing slightly displaced from their expected positions. Their light bent as it passed near the sun. The result electrified the scientific world. Gravity, it seemed, could bend light. This was impossible under Newton's framework, where light, having no mass, should remain unaffected by gravitational force. But in Einstein's geometry, mass was irrelevant. Light followed spacetime curvature itself. The universe had revealed that gravity reshaped not only motion, but the pathways of illumination. As the theory of general relativity matured, more implications unfolded. Time itself was affected by gravity. Clocks positioned near massive objects ticked more slowly than those farther away. The deeper the curvature, the slower time flowed. Gravity was not just bending space, it was sculpting time. Space-time, once thought of as static backdrop, became dynamic terrain. Hills and valleys formed by mass and energy. Planets moved through these valleys. Light curved along their slopes. Time thickened within their depths, and at the extreme end of curvature lay black holes, regions where space-time folded so steeply that escape became impossible. Not even light could climb out of their geometric well. Black holes were not cosmic vacuum cleaners pulling everything inward. They were points where space-time geometry collapsed into profound curvature. Objects crossing their boundary, the event horizon, simply followed space-time paths that led inward with no outward route available. Gravity here was not stronger force. It was deeper geometry. Einstein's equations described how mass and energy influenced space-time curvature through complex mathematical relationships. Though difficult to visualize directly, they revealed a universe far more fluid than previously imagined. Galaxies bent space-time across enormous scales. Clusters of galaxies created gravitational landscapes shaping cosmic structure. Even the expansion of the universe itself interacted with gravitational geometry. Gravity was no longer a local interaction between objects. It was a global shaping of reality's fabric. One of the most haunting predictions of general relativity involved gravitational waves, ripples in space-time generated by massive accelerating bodies, such as merging black holes. These waves would travel outward at the speed of light, stretching and compressing space-time as they passed. For decades they remained theoretical, too subtle to detect. Then, in 2015, instruments measured space-time ripples from colliding black holes over 1 billion light-years away. Humanity had, for the first time, detected the trembling of space-time itself. Gravity had become vibration. Einstein's reimagining transformed the philosophical meaning of gravity as well. Under Newton, gravity was interaction between objects. Under Einstein, gravity was dialogue between matter and geometry. Mass shaped spacetime. Spacetime shaped motion. Reality became reciprocal. Nothing existed independently of the fabric it inhabited. Even emptiness was not truly empty. It possessed structure, curvature, responsiveness. This shift dissolved the idea of space as passive void. Space became active participant. Time became elastic dimension. Together they formed a living geometry. In this framework, motion was no longer caused by force, but by following natural paths. Geodesics within curved spacetime. Nets did not resist gravity. The elegance of this view lay in its quietness. Gravity no longer required invisible tethers stretching across distance. Objects simply moved along the contours of the cosmic fabric. The universe became less mechanical, more sculptural. Matter carved reality. Light traced its curves. Time deepened in its wells. And through it all, gravity whispered rather than pulled. Einstein's radical shift did not erase Newton's work. It refined it. In everyday conditions where masses and velocities are moderate, Newtonian gravity remains an excellent approximation. But in regions of extreme mass, speed, or precision, space-time curvature reveals deeper truth. Mercury's anomalous orbit, long unexplained, aligned perfectly with Einstein's equations. Light bending near stars matched prediction. Time dilation near massive bodies was confirmed. Gravity, once treated as force, had revealed itself as geometry. The implications continue unfolding even now. Cosmologists study how space-time curvature shapes cosmic expansion. Astrophysicists map gravitational lensing to locate unseen matter. GPS satellites adjust for relativistic time shifts caused by Earth's gravity. Everyday technology quietly relies on Einstein's insight. Yet beyond utility lies philosophical wonder. If space-time can curve, what defines straightness? If time flows differently depending on gravity, what is simultaneity? If mass shapes reality's geometry, then presence itself sculpts existence. Gravity becomes less like pull, more like imprint. Mass leaves indentation in the universe. Motion follows those impressions. And so Einstein's radical shift transformed gravity from invisible force into cosmic architecture. A geometry written not in lines, but in curvature. Not in equations alone, but in the very structure of reality. Where Newton saw attraction, Einstein saw terrain. Where Newton imagined threads, Einstein revealed fabric. And in that fabric, bent by stars and folded by black holes, the universe whispered its deeper design. A silent architecture shaped by mass, guiding motion through curves too vast to see, yet precise enough to govern everything from falling apples to the slow dance of galaxies. For most of human history, space and time were imagined as completely separate experiences. Space was where things existed, the distance between objects, the vastness between stars, the emptiness surrounding planets. Time, meanwhile, was something that flowed, a steady invisible river carrying events from future into present, from present into past. One was location, the other was duration. They felt distinct, independent, almost unrelated. You could move through space, but never through time. You could wait through time, but remain still in space. The two seemed to belong to different categories of reality. This separation felt intuitive because it matched everyday experience. When you walked across a room, you traveled through space. When you waited for night to fall, you moved through time. One required motion, the other required patience. They did not appear to overlap. Clocks measured time, rulers measured space, calendars tracked duration, maps tracked distance. The tools themselves reinforced the belief that these dimensions were fundamentally different. Even Newton's physics preserved this division. Space was an unmoving stage, vast, absolute, unaffected by what occurred within it. Time flowed uniformly everywhere, independent of motion or gravity. Two observers, regardless of where they stood or how they moved, would agree on the passage of seconds. This framework worked well for everyday motion. Apples fell, planets orbited, projectiles followed predictable arcs, space hosted motion. Time measured it. But subtle inconsistencies emerged when scientists began studying light and extreme speeds. Experiments revealed something deeply unsettling. The speed of light was constant for all observers, regardless of how they moved. Whether you chased a beam of light or stood still, its speed remained the same. This contradicted common sense. If you ran toward a moving object, you should measure it moving slower relative to you. But light refused this logic. To preserve the constancy of light's speed, something else had to adjust. That something turned out to be space and time themselves. Albert Einstein's special theory of relativity revealed that space and time were not independent. They were interwoven dimensions forming a single structure. Space-time. Instead of imagining 3 dimensions of space plus 1 separate dimension of time, reality functioned as a 4-dimensional continuum where location and duration were inseparable. Every event required both. If you described something happening, you had to specify not just where, but when. Remove either coordinate, and the event became undefined. A star exploding is not just a place in the sky. It is a moment. A person standing in a room is not just spatial position. It is temporal presence. Space-time unified these coordinates into a single fabric. In this fabric, motion through space affected motion through time. If you moved very fast through space, your experience of time slowed relative to someone stationary. Clocks traveling at high speed ticked more slowly. Astronauts moving near light speed would age less than people on Earth. Time was no longer universal. It was personal, dependent on motion within space-time. This realization alone transformed the concept of reality. Time could stretch, space could contract. Observers moving differently would measure different durations and distances, yet all measurements remained internally consistent within space-time structure. Distance and duration became exchangeable in certain contexts, part of the same geometric system. To visualize this, physicists began imagining space-time as a flexible fabric, not because it literally resembled cloth, but because fabric conveyed flexibility, continuity, and curvature. This fabric was not visible. It had no color, texture, or thickness, yet it defined the pathways along which all motion occurred. Planets, light, people, galaxies, all moved within space at time, tracing paths determined by its structure. Under Einstein's later theory of general relativity, this fabric gained another property. It could bend. Mass and energy did not merely exist within space-time. They influenced its shape. A massive object like a star created curvature around itself, altering the geometry of nearby space-time. Objects moving through that region followed curved paths, not because they were pulled by force, but because straight lines themselves had become curved. In flat space-time, the shortest path between 2 points is straight. In curved space-time, the shortest path becomes an arc. So when Earth orbits the Sun, it is not being tugged by invisible force. It is following the natural curvature created by solar mass, moving along the straightest possible path within a bent geometry. Space-time tells matter how to move. Matter tells space-time how to curve. This reciprocal relationship lies at the heart of modern gravitational understanding, but space-time's flexibility extends beyond curvature alone. It can stretch. On cosmic scales, the universe itself expands. Galaxies drifting apart not because they travel through space, but because space-time between them stretches. The fabric grows, carrying galaxies with it like dots on an inflating surface. This expansion affects light as well. As light travels through stretching space-time, its wavelength elongates, shifting toward red, a phenomenon known as cosmological redshift. Even illumination responds to space-time's elasticity. Then there are ripples. Gravitational waves. When massive objects accelerate violently, such as colliding black holes, they disturb space-time's fabric, sending waves outward. These ripples stretch and compress space itself as they pass, altering distances minutely but measurably. Instruments sensitive enough can detect these distortions, registering echoes of cosmic collisions billions of years old. Space-time is not static. It moves. It vibrates. It evolves. Time, too, behaves differently depending on curvature. Near massive bodies, time slows, a phenomenon called gravitational time dilation. Clocks positioned on Earth's surface tick slightly slower than those aboard satellites. Near black holes, the slowing becomes extreme. An observer far away might see time nearly freeze at the edge of the event horizon. So space-time is not merely geometric. It is experiential. Where gravity weakens, time flows more freely. Even human technology accounts for this. GPS satellites must adjust for both speed-based and gravity-based time dilation to maintain navigational accuracy. Without relativistic corrections, positioning errors would accumulate rapidly. Thus, space-time is not abstract philosophy. It is measurable reality influencing daily life. Yet its scale remains difficult to intuit because human perception evolved for slow speeds and modest masses. We live in regions where space-time curvature is gentle, where relativistic effects are subtle. Only near massive bodies or at extreme velocities does space-time reveal its flexibility. Dramatically, still, its structure is always present. Every step you take traces a path through space-time, not just space. Every heartbeat occurs at a coordinate in the four-dimensional continuum. You are not merely located, you are located when. This fusion dissolves the idea of universal now. Events that seem simultaneous from one perspective may occur at different times from another moving viewpoint. Space-time reorganizes simultaneous into relativity. Past, present, and future become dependent on motion and position. Some physicists even describe the universe as a block, space-time, where all events past and future coexist within the four-dimensional structure. Time does not flow. Consciousness moves along its path. Whether philosophical or physical, this perspective deepens space-time's mystery. It is not simply a container. It is the framework within which existence unfolds. Flexible, responsive, shaped by mass, guiding motion, stretching across cosmic distances, curving around stars, rippling through collisions, slowing clocks, bending light, and yet utterly invisible. You cannot see space-time directly. You perceive its influence, gravitational pull, orbital motion, time dilation, but never the fabric itself. It is inferred through behavior, revealed through mathematics, confirmed through observation. Like wind seen only through moving leaves, or current sensed through drifting boats. Space-time whispers through motion. Its curvature explains why planets orbit. Its stretching explains cosmic expansion. Its ripples explain gravitational waves. Its time dilation explains relativistic aging. What once seemed separate, space as distance, time as duration, now appears unified, interdependent, a single fabric with four dimensions, flexible enough to bend under stars, subtle enough to ripple under black hole mergers, vast enough to contain every event that has happened or will happen. Within this fabric, nothing is truly still. Even stationary objects move through time. Even motion through space alters temporal flow. You exist along a continuous path, a world line, tracing your journey through space-time from birth to death. Gravity shapes that path by shaping the fabric itself. So when you stand on Earth, you are not being pulled downward by force alone. You are following the natural curve of space-time created by planetary mass. Your orbit around the sun is geometry expressed as motion. Your aging rate is geometry interacting with gravity and velocity. Space-time is not distant abstraction. It is the medium of existence, the quiet structure beneath all events. A flexible cosmic fabric where space and time are no longer separate threads, but interwoven strands, stretching, curving, rippling in response to matter and energy. And within its vast silent geometry, every motion, from drifting galaxies to falling leaves, unfolds along paths written not by force alone, but by the shape of reality itself. Imagine a wide, quiet surface stretched tightly across a frame, a smooth sheet pulled flat so that at first glance it appears perfectly level. There are no dips, no folds, no distortions. If you were to place a small marble on it, the marble would rest wherever you set it. If you nudged it gently, it would roll in a straight line. Now place something heavier at the center, a solid iron ball. Slowly, carefully, you set it down. The surface changes. The once flat sheet sinks beneath the weight. A shallow depression forms, deepening toward the center. The fabric stretches inward, curving gently downward. Nothing magical has happened. The sheet has not been pulled by invisible strings. It has responded to weight. Its geometry has changed. Now release the marble again, but this time near the heavy ball. Instead of traveling straight, it begins to curve inward. If pushed with the right speed, it may circle the depression, tracing looping paths around the heavier mass. It appears as though the heavy ball is pulling the marble inward. But look more closely. The marble is not being dragged across the sheet by some hidden force. It is simply following the curved surface beneath it. What once would have been a straight path is now bent, because the geometry has changed. The marble moves along the natural slope created by the depression. This quiet image, a stretched sheet and a heavy ball, has become one of the most common ways to visualize Einstein's idea of gravity. In this analogy, the sheet represents space-time, the unified fabric of space and time. The heavy ball represents a massive object like a star or planet. The marble represents a smaller object, perhaps a planet, moon, or asteroid. The depression in the sheet is not gravity as a pulling force. It is curvature. The mass has reshaped the surface, and the smaller object moves along the curved path. This analogy is not perfect, but it offers something invaluable, a calm visual of geometry replacing force. For centuries, gravity had been imagined as attraction, as if invisible hands reached out from one mass to another. The sun pulled Earth, Earth pulled the moon. Objects were tugged across emptiness, but in Einstein's view, nothing is reaching across space. Instead, mass changes the shape of spacetime itself. Objects move along that shape. The sheet bends, paths curve, motion follows geometry. In the rubber sheet image, the heavy ball does not chase the marble. It does not send signals commanding it inward. It simply sits, altering the surface around it. The marble, following the straightest possible route within that curved surface, appears to orbit. This is the crucial shift. What looks like attraction is really motion along curved terrain. To understand this more deeply, imagine that the sheet is not visible. You can only observe the marble's motion. If you see it curve inward, you might conclude there is a pulling force at work. But if you could see the depression beneath, you would realize the marble is not being pulled. It is responding to the slope. In everyday life, we often confuse slope with force. A ball rolling downhill accelerates not because something reaches out to grab it, but because the surface guides its motion. Gravity, in Einstein's framework, is similar. Space-time slopes around mass. Objects roll along those slopes. Now imagine increasing the mass of the central object. The sheet dips more deeply. The curvature becomes steeper. A marble placed nearby spirals inward more quickly. If placed too close, it cannot escape the depression at all. This mirrors what happens near extremely massive objects like black holes. The curvature becomes so steep that all paths lead inward. There is no outward slope available. The analogy remains gentle, yet its implications are profound. Planets orbit stars not because they are tethered, but because they move along curved spacetime. Their forward motion combined with curvature produces orbit, a continuous falling that never quite reaches the center. If you roll a marble fast enough along the edge of the depression, it may circle repeatedly, neither escaping nor plunging inward. It is falling sideways, always drawn along the curve. This is how Earth orbits the Sun. Earth moves forward through space. The Sun's mass curves space-time. Earth follows that curvature, tracing an elliptical path. No force pulls them across emptiness. The path itself is curved. The rubber sheet analogy also helps explain gravitational lensing, the bending of light near massive objects. Imagine drawing a straight line across the flat sheet. Now add the heavy ball. The line, following the surface, curves around the depression. Light traveling near a massive star does something similar. It follows the straightest possible path within curved space-time, which appears bent to distant observers. Even light, which has no mass, responds to curvature because it travels along space-time's geometry. This is one of the most striking consequences of Einstein's shift. Gravity affects not just objects with mass, but the structure of space and time through which everything moves. Returning to the sheet, consider placing multiple heavy balls on it, representing several stars or planets. The surface now contains overlapping depressions. The geometry becomes complex. A marble moving through this terrain responds to combined curvature, its path shaped by all masses present. This reflects how gravitational fields interact in reality. Multiple bodies contribute to spacetime's curvature. Motion emerges from the combined landscape. What feels like a web of forces becomes a sculpted surface. The rubber sheet image is limited in one important way. It uses gravity, Earth pulling downward, to create the depression. In reality, space-time curvature does not require external gravity to bend. It bends because mass tells it to. The analogy relies on familiar physics to illustrate unfamiliar physics. Still, its calm simplicity remains powerful. Picture the sheet not as two-dimensional but as representing a four-dimensional fabric. We cannot easily visualize four dimensions, so we borrow the sheet as a metaphor. The true curvature of space-time involves time as well as space. When the sheet dips, Not only space curves, time flows differently within the depression. Near a massive object, time slows compared to regions farther away. The marble near the center experiences slightly different timing than one at the edge. The slope is not only spatial but temporal. This adds depth to the analogy. The depression is not merely a valley in space, it is a thickening of time. Mass changes the geometry of both. As you imagine the marble circling the heavy ball, remember that its path is not forced. It is natural. It follows the straightest possible route in curved terrain, what physicists call a geodesic. On a flat sheet, a straight line is obvious. On a curved surface, the straightest path may appear curved to outside observers. Airplane routes over Earth demonstrate this. The shortest path between two cities on a globe is not a straight line on a map. It curves across latitudes. That curve is straight within spherical geometry. Similarly, planetary orbits are straight within curved spacetime. The rubber sheet analogy invites a gentle reorientation of intuition. Instead of imagining forces pulling objects across space, imagine space itself shaping their motion. Instead of tension, think architecture. When the heavy ball rests on the sheet, it does not strain to hold the marble in orbit. It simply exists, reshaping the surface. The marble's motion emerges from geometry, not command. This perspective changes the emotional tone of gravity. It becomes less like invisible tension and more like silent guidance. Mass leaves imprint, motion follows imprint. The universe becomes sculptural rather than mechanical. In this view, gravity is not something that acts at a distance. It is something that defines local shape. If you were small enough to live on the sheet, you would not see the depression. Directly, you would experience it as curved motion. You might deduce the curvature by observing trajectories. That is precisely what scientists do. They infer space-time curvature by measuring motion, the bending of light, the orbit of planets, the timing of pulsars. The sheet itself remains invisible. Only behavior reveals its form. The analogy also helps explain why orbiting bodies do not spiral immediately inward. If the marble is given sufficient sideways speed, it continually falls around the depression rather than into it. Likewise, Earth's forward velocity balances space-time curvature, creating stable orbit. Too little speed and it would fall inward. Too much speed and it would escape. Balance creates dance. Curvature creates pathway. Forward motion sustains orbit. The simplicity of the rubber sheet hides extraordinary depth. Beneath its calm image lies a radical idea. Gravity is geometry. Massive objects bend the cosmic fabric. Planets and light follow that bending. Time flows differently within it. Ripples travel across it when massive bodies accelerate. And through it all, there is no pulling hand. Only curved paths, traced through flexible structure. When you imagine the sheet settling quietly under the heavy ball, picture the universe doing the same. Stars dimpling space-time, galaxies creating vast basins of curvature, black holes forming steep wells where geometry deepens beyond return. Yet the motion remains graceful. Planets orbit in silent arcs, light curves gently around stars. Galaxies cluster along spacetime's contours, all because the fabric bends. The rubber sheet analogy does not capture every detail of general relativity. It simplifies dimensions. It borrows gravity to explain gravity. But as a mental doorway, it opens something essential. It shifts intuition. It replaces pulling with bending. It invites you to see motion as response to shape rather than force. In that quiet shift lies one of the most beautiful ideas in physics. The universe is not held together by invisible strings, but shaped into pathways by the presence of mass. The sheet bends. The marble rolls. The orbit forms. And gravity, once imagined as attraction across emptiness, becomes something more serene. The natural curve of reality guiding everything along its silent, sculpted path. There was a time when light was thought to be beyond gravity's reach, something too pure, too weightless to be influenced by the pull that governed planets and falling stones. Gravity, in Newton's universe, acted between masses. It required substance, matter, weight. Light, having none, should travel untouched, moving in perfect straight lines across the vast emptiness of space. This belief felt natural. When you shine a beam across a dark room, it does not curve downward. When sunlight enters through a window, it spreads in straight shafts. Light appears obedient only to mirrors and lenses, bending when refracted through glass, but otherwise moving with unwavering direction. So for centuries it was assumed that gravity ruled matter, while light traveled freely, unaffected, untethered. But Einstein's reimagining of gravity as curvature in spacetime quietly changed this expectation. If gravity were a force pulling on mass, light might escape its influence. But if gravity were the bending of spacetime itself, the shaping of the very geometry through which everything moved, then light would have no choice but to follow those curves. Light, after all, always takes the straightest possible path. But what counts as straight depends on the shape of spacetime. On a flat surface, straight is obvious. On a curved surface, straight may appear bent to outside observers. Airplane routes across Earth illustrate this well. The shortest path between two cities is not straight on a flat map, but curved along the globe's geometry. Light behaves similarly in curved spacetime. It travels straight, but straight within curvature becomes arc. This phenomenon is known as gravitational lensing. Massive objects like stars or galaxies bend the spacetime around them. Light passing through that region follows the curved geometry, causing its path to deflect. To distant observers, the light appears bent, as though pulled when in fact it is simply tracing spacetime's contour. Einstein predicted this effect as one of the first observable consequences of general relativity. If his theory were correct, starlight passing near the sun should bend slightly due to solar mass curving spacetime. The deflection would be tiny, almost imperceptible, but measurable with careful observation. Testing this prediction required a rare alignment. Normally, the sun's brightness overwhelms the stars behind it, making their positions impossible to measure. But during a total solar eclipse, the moon blocks the sun's light, briefly revealing stars near its edge. If Einstein was right, those stars would appear slightly shifted from their normal positions because their light had curved while passing near the sun. In 1919, expeditions led by astronomer Arthur Eddington traveled to observe a solar eclipse. One team to the island of Principe off the west coast of Africa, another to Sobral in Brazil. Their mission was delicate. They needed clear skies, precise instruments, and photographic plates capable of capturing faint starlight near the eclipsed sun. When the eclipse arrived, they recorded images of the surrounding stars. Later, they compared these photographs to reference images taken when the sun was elsewhere in the sky. The results were extraordinary. The stars appeared displaced, shifted outward from the sun's edge by exactly the amount Einstein's equations predicted. Light had bent. Not metaphorically, physically. The universe had confirmed that spacetime curvature influenced even massless illumination. This observation electrified the scientific world and propelled Einstein into global recognition. Newspapers declared that gravity could bend light, that space itself was curved. For the first time, humanity had witnessed light responding to the geometry of spacetime. Gravitational lensing did not stop at solar eclipses. As telescopes improved, astronomers began observing far more dramatic examples across the cosmos. Massive galaxies containing billions of stars create immense spacetime curvature. Light from objects behind them, more distant galaxies or quasars, bends around this curvature as it travels toward Earth. Sometimes the bending is subtle, slightly distorting the background object's shape. Other times it is spectacular. If alignment is precise, the foreground galaxy acts like a cosmic lens, magnifying and warping the background light into arcs, rings, or multiple images. These formations are called Einstein rings when they form near-perfect circles. Light wrapped around spacetime curvature like a halo. In these moments, gravity behaves exactly like optical glass, not by refracting light through material, but by curving the space through which light travels. The analogy is poetic. The universe itself becomes a lens. This cosmic lensing has become one of astronomy's most powerful tools. By studying how light bends, scientists can measure the mass of galaxies, including invisible mass. Dark matter, which emits no light, reveals its presence through gravitational lensing. Its mass curves spacetime, bending background light in detectable ways. Thus, lensing allows astronomers to map unseen structures across the universe. Light becomes probe. Curvature becomes measurement. The bending of illumination becomes evidence of hidden matter. On smaller scales, gravitational lensing can magnify distant galaxies, allowing telescopes to observe objects that would otherwise be too faint. The curvature acts like a natural telescope, amplifying ancient light that has traveled billions of years. So when we look through gravitational lenses, We are not just seeing distorted images. We are seeing deeper into time. Light bent by mass carries information from epochs long past. In extreme cases, gravitational lensing produces multiple images of the same object. Light traveling along different curved paths arrives at Earth from slightly different directions, and even at slightly different times. Astronomers have observed quasars appearing duplicated or quadrupled around foreground galaxies. 4 images of the same luminous source, each following a different space-time route. Time delays between these images can be measured, offering insights into cosmic expansion and space-time geometry. All of this emerges from one quiet principle. Light follows curvature. It obeys geometry. Returning to the solar eclipse, that first confirmation remains symbolically powerful. For centuries, eclipses had inspired myth, fear, and wonder. In 1919, one became a laboratory for testing the shape of reality itself. When the moon slid before the sun and darkness briefly fell, it revealed not divine omens, but geometric truth. Starlight curved, space-time bent, gravity extended beyond matter into illumination. The eclipse became proof that the universe's structure was not rigid, but responsive. Even today, eclipse observations continue refining our measurements of gravitational light. Bending, though modern instruments can detect lensing without needing the moon's shadow. Still, the historical moment remains profound. Humanity using celestial alignment to glimpse space-time curvature. Light bending also affects how we perceive black holes. Though black holes emit no light, the space-time around the FM bends, passing illumination dramatically. This creates glowing rings of distorted light, photons orbiting briefly before escaping. Images captured by the Event Horizon Telescope reveal these luminous halos, visualizing curvature at its most extreme. Light itself outlines gravity's depth. In neutron stars and galaxy clusters, similar distortions occur. Arcs of light stretched across the sky, faint but measurable. Each arc is a map of curvature. Each distortion is geometry made visible. The phrase "light bends too" carries philosophical weight as well. Light has long symbolized straightness, purity, directness. Yet in curved space-time, even light must yield to geometry. Nothing escapes space-time structure. Not matter, not radiation, not time. All follow the fabric's shape. This realization deepens gravity's quiet authority. It is not merely a force acting on heavy things. It is the architecture within which all motion unfolds. Light, traveling at the universe's speed limit, still cannot ignore curvature. It traces space-time's design with silent obedience, and through its bending, it reveals that design to us. When astronomers map gravitational lensing patterns, they are effectively tracing the invisible topography of space-time. Hills, valleys, and wells carved by mass across cosmic distances. We cannot see space-time directly, but we can see how light moves within it. In this way, illumination becomes cartography. Every curved beam is a contour line on the universe's geometric map. From the delicate deflection near our sun to the vast arcs around galaxy clusters, gravitational lensing confirms again and again that Einstein's vision holds true. Gravity does not simply pull. It shapes, it sculpts the routes along which even light must travel. So when you imagine a beam of starlight crossing the universe, do not picture it moving along rigid, straight corridors. Picture it gliding across a flexible fabric, dipping near stars curving around galaxies, rippling past gravitational waves. Its journey is not linear but sculpted. Its path not commanded but guided. And occasionally, when alignment allows, that curved journey becomes visible to us, during an eclipse, through a telescope in a luminous arc stretched across the night sky. In those moments, gravity's quiet geometry reveals itself not through falling apples or orbiting planets, but through the bending of light itself. A whisper of curvature traced in illumination, confirming that space-time is not only the stage of the universe, but its silent, shaping lens. There is a common image people carry when they first hear the words black hole. It is dramatic, almost violent, a cosmic vacuum cleaner roaming the universe, sucking in anything that wanders too close. Stars spiral helplessly inward. Light is swallowed. Entire solar systems are devoured without resistance. The picture feels chaotic, hungry, destructive. But this image, though vivid, is deeply misleading. Black holes do not roam space, consuming everything in their path. They do not pull objects from vast distances any more strongly than other objects of equal mass. If our sun were replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as it does now. The gravitational pull at that distance would be unchanged. What makes a black hole extraordinary is not that its gravity reaches farther, but that its gravity curves space-time more deeply than anything else we know. A black hole is not defined by appetite. It is defined by geometry. To understand this, it helps to return to the idea that gravity is not a pulling force but a bending of space-time. Massive objects curve the cosmic fabric. Planets follow those curves. Light bends within them. A black hole represents the most extreme curvature possible, a region where space-time folds so steeply inward that all paths lead deeper inside. Imagine space-time as a landscape rather than a flat surface. Stars create gentle valleys. Planets form shallow dips. But a black hole forms a well so deep that once you descend past a certain boundary, there is no upward slope remaining. Every possible path points inward. That boundary is called the event horizon. The event horizon is not a physical surface. There is no wall, no barrier, no material shell. It is a geometric threshold, the point where space-time curvature becomes so extreme that escape trajectories cease to exist. Outside the event horizon, an object can still move away if it has sufficient velocity. Inside, even light, the fastest thing in the universe, cannot find a path leading outward, not because it is being pulled back, but because outward paths no longer exist. Space-time itself is curved inward beyond recovery. If you could hover just outside the event horizon, you would notice strange effects. Time would appear distorted. Light from the universe beyond would seem accelerated. Clocks farther away would tick faster than your own. To a distant observer watching you approach the horizon, you would appear to slow down, your motion stretching across time, never quite crossing the boundary. This is gravitational time dilation at its most extreme. Time itself bends along with space. Crossing the event horizon, however, would feel locally uneventful, assuming the black hole is large enough. There would be no sudden jolt, no visible line. You would pass the threshold quietly, unaware that escape had become impossible. Inside, all future directed paths lead inward toward the singularity, the region where curvature becomes infinite, where space-time as we understand it collapses beyond description. The singularity is not simply a point in space. It is a point where geometry breaks down, where known physics can no longer describe conditions. Density becomes immeasurable. Curvature becomes infinite. Time and space exchange roles in ways still not fully understood, but even the singularity is less important observationally than the horizon itself, the boundary separating escapable geometry from inescapable geometry. This is what defines a black hole, not destruction but entrapment within space-time curvature. The vacuum cleaner metaphor fails because it implies active suction. In reality, objects must approach very close before capture occurs. If you replaced Earth with a black hole of equal mass, the Moon would continue orbiting normally, because curvature at that distance would remain unchanged. Black holes do not suck. They curve. Only when you approach the deep well does escape velocity exceed the speed of light, not because gravity pulls harder outward, but because space-time tilts inward so steeply that outward motion becomes geometrically impossible. Another way to imagine this is through rivers. Picture space-time flowing like water toward the singularity. Far away, the flow is gentle. You could swim upstream easily. Closer in, the current strengthens. At the horizon, the flow inward equals the speed of light. Beyond that point, the current exceeds light speed, not in violation of relativity, because it is space-time itself moving. No swimmer, no signal, no beam of light can move outward against that inward flow. Escape is not resisted. It is undefined. Black holes also distort light dramatically near their horizons. Photons can orbit temporarily, circling the black hole along curved space-time paths before escaping or falling inward. This creates the luminous photon ring, seen in black hole imagery, a glowing halo marking the last stable orbits of light. Even illumination becomes trapped in geometry. Despite their reputation as devourers, black holes are often quiet, unless surrounded by matter. If isolated in empty space, a black hole would be invisible, detectable only through its gravitational influence. But when matter approaches, it forms an accretion disk, a spiraling ring of superheated gas glowing intensely as friction and gravitational compression raise temperatures to extreme levels. This glow is not the black hole itself, but matter heating as it descends through curved spacetime. Jets of energized particles may erupt from the poles, powered by magnetic fields interacting with rotational energy. These jets can extend across thousands of light years. Yet even here, the black hole is not actively consuming. It is shaping spacetime so deeply that matter naturally flows inward. Geometry drives motion, not hunger. Black holes also merge, producing gravitational waves, ripples in spacetime emitted as their immense curvatures interact and settle into new equilibrium. When detected on Earth, these waves represent distortions of spacetime itself, echoes of extreme geometry reshaping the cosmic fabric. Even time behaves differently near black holes. To distant observers, objects falling inward appear frozen near the horizon, their light red shifting and dimming. From the falling object's perspective, however, time proceeds normally, though the outside universe appears accelerated. Space-time near black holes becomes so warped that perspectives diverge dramatically. This leads to philosophical reflections as well as physical ones. If escape becomes impossible beyond the horizon, information entering a black hole appears lost. Yet quantum physics suggests information must be conserved. This paradox, the black hole information problem, remains one of the deepest unsolved questions in theoretical physics. Some theories propose information is encoded on the horizon's surface. Others suggest it escapes through subtle quantum processes like Hawking radiation, a faint emission caused by quantum effects near the horizon. Hawking radiation implies black holes are not eternal. Over immense timescales, they evaporate, losing mass gradually until they disappear. Even extreme geometry evolves, yet the core insight remains unchanged. Black holes are not cosmic predators roaming space, but regions where space-time curvature becomes so profound that outward paths vanish. They are wells in reality's fabric, places where geometry deepens beyond return. They remind us that gravity is not merely force but structure, capable of folding the universe inward on itself. When you imagine a black hole, picture not suction but descent, not pulling but tilting, not devouring, but curving. A place where space-time slopes so steeply that all journeys lead inward. And within that inward geometry, time slows, light bends, and the familiar rules of distance dissolve into deeper, stranger architecture, the ultimate expression of gravity's silent design. There was a time when gravity was imagined as perfectly steady, a constant, unchanging curvature in space-time shaped by mass and energy. Stars bent the cosmic fabric. Planets traced those curves. Galaxies sculpted vast gravitational landscapes. But these structures, though dynamic in motion, were thought to produce static geometry, valleys and wells that guided movement without themselves trembling. Einstein's equations, however, hinted at something quieter and more subtle. If space-time could bend, could it also ripple? If mass could curve the fabric, could accelerating mass disturb it, sending waves outward the way a moving object disturbs water? The mathematics suggested yes. When massive bodies accelerate, especially in asymmetric or violent motion, they generate distortions in spacetime that propagate outward at the speed of light. These distortions are gravitational waves. They are not waves traveling through spacetime like sound through air. They are waves of spacetime itself, oscillations in the fabric of reality. Imagine a still pond at night. The surface is calm, reflective, undisturbed. Now drop a stone into it. Concentric ripples spread outward, carrying energy across the water. Gravitational waves are similar, but instead of water, it is spacetime that ripples. Instead of stones, the sources are colossal cosmic events, colliding black holes, merging neutron stars, supernova explosions, or rapidly rotating massive bodies. Among these, black hole mergers produce the most powerful waves we have observed. Picture two black holes orbiting one another, a binary system formed long ago when two massive stars collapsed. They circle slowly at first, separated by immense distance, each carving deep curvature into spacetime. As they orbit, they emit gravitational waves continuously, losing orbital energy in the process. This loss is subtle at first. The waves are faint, the energy small relative to their mass. But over millions or billions of years, the orbit shrinks. The black holes spiral closer, Their orbital speed increases. Their curvature fields interact more intensely. Space-time around them begins to churn. As the distance closes, the motion accelerates dramatically. The two wells in space-time draw nearer, their geometries overlapping, distorting, amplifying. The system becomes a storm of curvature. In the final moments before merger, they orbit each other at significant fractions of light speed, completing revolutions in milliseconds. Space-time trembles violently. Then comes the collision. The two horizons merge into one. The geometry reshapes abruptly, releasing an immense burst of gravitational energy, converted not into light, but into space-time waves radiating outward. For a brief instant, the power emitted in gravitational waves can exceed the combined light output of all stars in the observable universe. Yet the waves themselves remain extraordinarily subtle. By the time they reach distant observers, they stretch and compress space-time minutely, altering distances by fractions smaller than atomic nuclei. Detecting them required instruments of almost unimaginable precision. For decades after Einstein predicted gravitational waves in 1916, they remained theoretical. Scientists debated whether they were physically real or merely mathematical artifacts. Indirect evidence emerged in the 1970s when astronomers observed a binary neutron star system losing energy, exactly as gravitational wave emission predicted. But direct detection proved elusive. To measure space-time distortions smaller than a proton's width required technological sensitivity beyond anything previously built. That changed in 2015. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first direct gravitational waves. Two detectors, one in Louisiana and one in Washington state, measured synchronized distortions in space-time caused by a black hole merger 1.3 billion light-years away. The signal lasted less than a second, a rising chirp as the black holes spiraled together. Yet within that fleeting vibration lay confirmation of one of Einstein's most profound predictions. Space-time had rippled, the waves had traveled for over 1 billion years, crossing galaxies, voids, clusters, until they passed through Earth, stretching and compressing reality itself by infinitesimal amounts. When converted into sound frequencies, the signal produced a soft ascending tone. The universe's geometry briefly translated into audible form. It was the first time humanity had heard space-time. Gravitational waves differ fundamentally from electromagnetic waves like light or radio. Light interacts with matter easily. It can be absorbed, scattered, blocked. Gravitational waves interact extremely weakly, passing through stars, planets, even entire galaxies almost unaffected. They carry pristine information about their sources, unblurred by intervening matter. This makes them powerful cosmic messengers. Through gravitational wave astronomy, scientists can observe events invisible to traditional telescopes. Black hole mergers emit no light, yet produce immense space-time ripples. Each detection reveals mass, spin, distance, and energy of the merging bodies. It is a new sense, not seeing the universe, but feeling its vibrations. As detectors improve, more events are recorded. Black holes of different sizes, neutron star collisions producing both gravitational waves and electromagnetic flashes, hybrid mergers. Each wave carries signature patterns, space-time fingerprints of the event that created it. The waves themselves are gentle by the time they arrive. As one passes through Earth, distances stretch in one direction while compressing in another, oscillating rhythmically. You would never feel it. Your body, your surroundings, even atomic structures expand and contract together, leaving no internal reference to detect motion. Only laser interferometers measuring path lengths to astonishing precision can reveal the distortion. This gentleness contrasts with the violence of their origin. Colliding black holes, objects containing multiple solar masses compressed into city-sized horizons, releasing energy equivalent to several suns converted entirely into space-time waves. It is like a cosmic bell being struck, its vibrations traveling silently across the universe. Gravitational waves also reveal something profound about gravity itself. It is dynamic. Space-time is not static curvature frozen in place. It moves. It vibrates. It carries energy through geometry. This dynamism adds a new dimension to gravity's character. Not only does mass sculpt space-time, accelerating mass animates it. Curvature becomes motion. Geometry becomes wave. Some gravitational waves are primordial, relics from the early universe, produced fractions of a second after the Big Bang. Detecting these would allow scientists to probe conditions at the dawn of spacetime itself, energies and geometries unreachable by any other means. Future detectors, both ground-based and spaceborne, aim to measure these faint ancient ripples. In this way, gravitational waves extend astronomy beyond light into pure geometry. They allow us to study the universe through its structure, rather than its illumination. Returning to the merging black holes. After collision, the newly formed black hole vibrates briefly, settling into stable curvature. This phase is called the ring-down, like a struck bell fading into stillness. Even spacetime must stabilize after violent distortion. The waves carry away excess energy, leaving equilibrium behind. Across billions of light years, these waves travel undiminished, silent, invisible, yet real. They pass through galaxies unnoticed, through planetary systems undetected, through human bodies unfelt. But instruments listening carefully can sense their arrival, faint tremors in the cosmic fabric. Each detection confirms that gravity is not merely curvature but living geometry. Capable of motion, resonance, and transmission, it transforms our understanding of the universe from static sculpture into dynamic symphony. Stars bend spacetime, black holes deepen it, collisions ring it like a bell, and gravitational waves carry those resonances outward, whispers of cosmic events long concluded. They are messages written not in light, but in distortion. Travelers across billions of years, arriving as gentle oscillations in distance itself. The universe does not only shine, it vibrates, and through gravitational waves, we have learned to listen to the quiet music of spacetime. Ripples born in the darkest mergers, gliding across the cosmos, carrying the story of gravity's most extreme moments in waves too subtle to see, yet profound enough to reshape how we perceive reality's silent, trembling fabric. If you step outside on a clear night and look upward, the sky can feel scattered and spontaneous. Stars sprinkled across darkness without pattern, galaxies drifting like faint smudges, planets wandering quietly among fixed constellations. To the casual eye, the universe appears vast but unstructured, beautiful yet accidental. And yet beneath that apparent randomness lies order, not rigid like machinery but structured like architecture, not designed in the human sense, but shaped by invisible geometric rules that govern motion, balance, and form. Galaxies do not gather arbitrarily, planets do not orbit chaotically, clusters of stars do not drift without influence. Everything moves within a framework, a gravitational geometry that quietly determines pathways, stability, and structure. When Einstein revealed that gravity is curvature in spacetime, he transformed our understanding of the universe from a system of pulling forces into a vast architectural landscape. Mass bends spacetime. Spacetime shapes motion. From this reciprocal relationship emerges structure. Consider a single star forming within a cloud of gas and dust. The cloud, initially diffuse and chaotic, begins to collapse under its own gravitational curvature. Particles drift inward, following spacetime's gentle slope. As mass accumulates, curvature deepens. The collapse accelerates, but rotation prevents total inward collapse. As the cloud contracts, it spins faster, conserving angular momentum. The result is not a random cluster, but a flattened disk, encircling a growing star. Within that disk, further curvatures develop, small concentrations of mass carving local dips in spacetime. Dust gathers into clumps. Clumps become planetesimals. Planetesimals merge into planets. The architecture of a solar system emerges not from blueprint, but from geometry. Orbits settle into stable paths because space-time curvature defines allowable trajectories. Too close to the star, and curvature is too steep for stable orbit. Too far and gravitational binding weakens. Planets move along geodesics, the straightest paths within curved spacetime. Stability arises from shape. Zoom outward to the scale of galaxies. A galaxy is not simply a collection of stars. It is a gravitational system bound by space-time curvature, generated by both visible matter and invisible dark matter. Stars orbit the galactic center, not because they are tethered, but because the geometry of space-time within the galaxy forms a vast gravitational well. Spiral galaxies trace graceful arms, patterns emerging from rotational dynamics within curved space-time. These arms are not rigid structures, they are density waves, regions where stars cluster temporarily as they move through the galactic disk. Even these patterns are shaped by invisible rules: conservation of angular momentum, gravitational instability, curvature interactions. Elliptical galaxies lacking pronounced rotation form different shapes. Spherical or elongated, their structure determined by the geometry of initial collapse and subsequent mergers. Galaxy clusters gather into even larger formations, bound by curvature fields spanning millions of light years. Between clusters lie filaments, immense strands of matter tracing the cosmic web. The cosmic web itself resembles architecture on a grand scale, a network of filaments and voids, shaped by early density fluctuations, amplified by gravitational geometry. After the Big Bang, the universe was nearly uniform. Tiny variations in density existed, barely perceptible. Over billions of years, those slight differences grew under gravitational curvature, regions slightly denser than average curved spacetime a bit more strongly, attracting nearby matter. As matter accumulated, curvature deepened, drawing in more material. Like architectural supports strengthening over time, these regions evolved into galaxies and clusters. Meanwhile, underdense regions became voids, vast expanses with little matter, where curvature remained shallow. The large-scale structure of the universe is not random scattering, but patterned by geometry, a cosmic architecture built through curvature interacting with matter. Even dark matter, though invisible, contributes to this architecture. Its mass shapes spacetime just as visible matter does. Observations of gravitational lensing revealed dark matter halos surrounding galaxies, extended curvature fields, guiding stellar motion. Without dark matter's contribution, galaxies would not hold together as observed. Their rotational speeds require deeper curvature than visible mass alone can provide. Thus, unseen geometry stabilizes luminous structure. On smaller scales, architecture appears in orbital resonances. Moons orbiting planets sometimes settle into synchronized patterns, one completing 2 orbits for every orbit of another. These resonances arise from gravitational interactions shaping stable configurations. The system adjusts until geometric relationships produce long-term balance. Saturn's rings offer another example. Billions of particles orbit within specific bands, gaps appearing where gravitational interactions with moons create unstable curvature zones. The ring's delicate structure emerges from invisible geometric rules. Even planetary rings and asteroid belts follow architectural constraints defined by curvature and motion. Binary star systems, 2 stars orbiting one another, reveal gravitational symmetry in motion. Each star follows a path around a shared center of mass, their trajectory shaped by mutual curvature. On the largest scales, superclusters of galaxies form sprawling complexes, not because of attraction in the simple sense, but because space-time curvature guides matter into specific regions over cosmic time. The universe behaves less like a random explosion and more like a self-organizing structure governed by geometric constraints. Architecture does not imply intention. It implies structure arising from rules. In human architecture, beams support weight, arches distribute stress, curves enhance stability. These principles reflect geometric realities, forces interacting within space. Cosmic architecture emerges similarly, but without conscious design. Curvature distributes motion. Rotation stabilizes structure. Energy conservation shapes pattern. Time allows geometry to evolve. Even black holes, the most extreme geometric features, contribute to cosmic architecture. At the centers of most galaxies lie supermassive black holes. Their curvature influences stellar motion and galactic dynamics. Jets emitted from active galactic nuclei can regulate star formation, shaping the galaxy's future structure. The architecture of a galaxy includes not just stars but feedback mechanisms, gravitational wells, and energy flows, all governed by geometry. Gravitational waves add another layer to this architecture. When massive objects merge, they do not merely collide. They reshape space-time structure and send ripples outward, redistributing energy across the cosmic fabric. The universe is not a static building. It is evolving architecture, dynamic, responsive, continuously reshaped by mass and energy. And yet, through all this change, patterns persist. Elliptical orbits, spiral arms, cluster filaments, orbital resonances. Gravitational lens arcs. These are not accidents. They are expressions of geometric rules playing out across time. Even chaos has boundaries defined by curvature. Planets cannot wander arbitrarily without encountering gravitational constraints. Stars cannot drift freely within galaxies without responding to curvature gradients. Space-time defines possible paths. Structure emerges. In this view, gravity is not merely force, but framework. The universe resembles a vast cathedral of geometry. Arches of orbit, pillars of clusters, vaults of curved space-time spanning unimaginable distances. Yet unlike stone cathedrals, this architecture breathes. It expands as the universe expands. It deepens where mass accumulates. It ripples where energy shifts. It ages as time flows. Every motion traces a line through this four-dimensional structure, a world line shaped by curvature. Even your own body participates. Earth's curvature defines your weight. The sun's curvature defines Earth's orbit. The Milky Way's curvature guides the solar system's path around the galactic center. We exist within layered architecture, nested curvatures shaping motion at every scale. This perspective changes how we perceive emptiness. Space is not empty stage. It is structured medium. The apparent void between galaxies is shaped by expansion and residual curvature from early density fluctuations. Even vacuum energy contributes to cosmic expansion, influencing the architecture's growth. The universe is less like scattered debris and more like evolving design shaped by consistent geometric principles. The rules are invisible, yet their effects are visible everywhere. From the graceful arc of a comet to the clustering of galaxies, from the stability of planetary systems to the formation of black holes, geometry governs outcome. Mass curves space-time. Curved space-time guides motion. Motion redistributes mass. Mass reshapes space-time. This loop continues across billions of years, constructing and reconstructing the universe's form. Architecture suggests stability, but cosmic architecture is fluid. Structures merge, collapse, reform. Galaxies collide and reshape. Stars explode and seed new systems. Yet through all transformation, the underlying geometric rules remain constant. They do not command, they constrain. Within those constraints, matter creates infinite variation. The universe, then, is not chaotic emptiness but sculpted vastness. Architecture without architect, structure without blueprint, governed by curvature and motion intertwined. Invisible geometric rules shape visible cosmic beauty. And when we look up at the night sky, we are not seeing scattered lights and darkness. We are seeing the luminous edges of a grand, silent architecture. Galaxies suspended within curvature, stars tracing arcs written by geometry, cosmic structure unfolding according to rules as quiet and consistent as the bending of space-time itself. As we drift back from curved light, orbiting worlds, and rippling space-time, one quiet truth remains: gravity is not a harsh pull, but a gentle shaping. The universe is not rigid or fixed. It bends, responds, and adapts to every presence within it. From stars to silence, everything moves along soft, geometric paths written into reality itself. So let your thoughts slow now, like planets settling into orbit. Let the vast architecture of space-time hold your mind in calm suspension. And as gravity quietly cradles worlds through the dark, allow it to cradle your rest as well, steady, weightless, and unhurried into sleep.